This video is going to be an explanation of how to compute the derivative of a multivariable function f from Rn to Rm. But first we're going to start with the simple case where n and m are both just 1. So in this case we say that f is differentiable at a point x naught if the limit x approaches x naught of f of x minus f of x naught divided by x minus x naught exists. And in this case, we say that this limit is equal to the derivative of f at x naught. So I'm going to rewrite this in a way that might seem unusual, but actually generalizes really well to higher dimensions. So we can rewrite this as the limit as x approaches x naught of f of x minus f of x naught minus m times x minus x naught divided by x minus x naught is equal to 0 for some m in R. And it turns out that this m is actually just f prime at x naught. So the reason why we do this is notice that linear transformations from R to R are of the form x goes to x times m for some real number m. So this is what we're going to want to generalize. The idea of a derivative as a linear transformation. Okay, so let's write the general version of f from Rn to Rm is differentiable at x naught, this time x naught is an element of Rn, if the limit x approaches x naught, f of x minus f of x naught minus t times x minus x naught, all divided by x minus x naught equals 0. And this doesn't really make sense because we're dividing a vector in Rm by a vector in Rn. So what we're going to do is take the Euclidean norm of the top and bottom. So the double bars denote the Euclidean norm. And this is just a generalization of the way you would find the length of a vector in 2 dimensions. It's the square root of x1 squared through xn squared. And then in this case, if f is differentiable, we say that t is the derivative of f at x naught, and we denote it by df at x naught. So I can plug different values of x in for x naught and get different df's. And t is some linear transformation from Rn to Rm. So you can see basically where the role that t is playing is the same as the role that m is playing in the one-dimensional case. Okay, so now our goal is to find the matrix of df at x naught. So first let's give the entries of this matrix names. So let's assume that df at x naught is equal to a11 all the way out to a1n, all the way down to am1, all the way down to amn. So meaning if the vectors ej are a basis for Rn and ei tilde are a basis for Rm, then df at x naught of ej is equal to a1j e1 tilde all the way out to amj, sorry, that should be an a, em tilde, i.e. the jth column of the matrix for df consists of the coefficients of the ei tildes in df at x naught of ej. So now let's relate these aij's back to f. So recall that 0 is the limit as x approaches x naught of f of x minus f of x naught minus df at x naught, x minus x naught, all divided by x minus x naught, and then we take the Euclidean norm of everything. So let's plug in x equals x naught plus h times ej. So we get 0 is the limit as h approaches 0 of the norm of f of x naught plus h of ej minus f of x naught minus df at x naught. So now x minus x naught is just h of ej, and I'm dividing by the norm of h of ej. And I can rewrite all of this as the limit as h approaches 0 of f of x naught plus h times ej minus f of x naught minus h df at x naught of ej, all divided by the absolute value of h, because the Euclidean norm of ej is just 1. So the Euclidean norm approaches 0 precisely when each component approaches 0. So this limit has to also hold for the components of the numerator. So the numerator is the absolute value or the Euclidean norm of some vector in Rm, and the limit also has to hold for the components, because if you go back to the definition of the Euclidean norm right here, the Euclidean norm of something is 0 exactly when all of its components are 0. So if I write f, I was just checking to see if I had done this yet, but I had not. So let's write f at x naught as a bunch of components. So because f at x naught is an element of Rm, I can write f as an m tuple of functions f1 through fm. So this limit being 0 is equivalent to the limit as h approaches 0 of fi of x naught plus h ej minus f at x naught minus, so now I need the ith, so this should be fi as well. Now I need the ith component of df at x naught of ej, but that's exactly aij. So this should be h times aij, all divided by, so this is exactly aij by this definition of aij here, and all divided by the absolute value of h. And that implies that 0 is equal to the limit as h approaches 0 of the same numerator, x0 plus hej minus fi of x0 minus haij divided by h with no absolute value. And I can rewrite this now as aij is equal to the limit as h approaches 0 of fi at x0 plus hej minus fi at x0 over h. So why is this so great? So if I were to write x0 out in vector form, so I'll call it x, or not vector form, but as a point in Rn, excuse me, it would be x1, x0, 1 through x0, n. Let's say those are the coordinates of x0. So then this right-hand side is precisely the limit as h approaches 0 of fi at x0, 1, all the way out to x0j plus h, all the way out to xn, x0n, minus fi at x0 divided by h. And this should be familiar to you as the partial derivative of fi in the direction of xj. So what this is telling me is that df at x naught is equal to the matrix whose entries are d by dfi by d by dxj. So this would be dfm by dx1 all the way out to dfm by dxn, which is what we've been wanting to show all along. And this matrix on the right-hand side has a special name. It's called the jacobian of f at x naught.